Resume recording. Yes, so professional. I have your chat up on a second monitor, so if you chat at me, then I will see it. Hopefully, you can also just interrupt. Okay, so an ordinal is a set that is transitive, right, and well ordered by the element relation. So examples. All of the natural numbers are ordinals, but so is omega, and so is the successor of omega, and so is the successor of the successor of omega, right? And we can keep going in that fashion. And we've also shown a bunch of other things, like if you have a set of ordinals and you take their union, then that's an ordinal. So it's called the supremum. So it's the least ordinal greater than or equal to everything in the original set. But to build anything beyond the natural numbers and then omega, omega plus, and so on, we actually need another axiom. So that's coming below. Okay, so we have ordinals. We compare them by the element relation, right? And we say that if an ordinal is in another one, then it's the smaller ordinal is in the bigger one. And there's a sense in which this is to do with the underlying well orders of the structures. So if you can think of an ordinal as measuring the length of a well order, right, of a list where you enumerate the things like one at a time, but potentially like it takes longer than forever, whatever that means, potentially longer than omega. All right, so then the smaller lists are in the bigger lists. And this relation is like a well order in that it's transitive, irreflexive, antisymmetric, trichotomy holds. Every set of ordinals has a least element, but it isn't a set because the collection of all ordinals is not a set, which I haven't. Well, I guess we have proved that, right? Because we've shown that if you have a set of ordinals, then there's an ordinal not in that set, right? So there is no set of all of them. All right, so if the set of all ordinals were a set, this would actually literally be a well order, but it isn't because well, in our sense, it would be a well order because it's a relation satisfying various properties. It's just not a relation. So us like looking at the set theory, we can like point at it and say that's a well order, but the set theory kind of doesn't see that it's a well order because it doesn't form it into a set. Okay. And anyway, so because the collection of all ordinals is well ordered, then we have this like correspondence between having a least counterexample to a claim and induction, right? If there's no least counterexample, then it must be true of everything because there's always a least element of every set. So we can do transfinite induction on the ordinals. So we can prove things about the ordinals by induction. It's just slightly more complicated because we have to deal with what's called the limit case of ordinals, right? So we've got the zero case, we've got the successor case, and we have the limit case. I should technically say non-zero limit case because zero is a limit according to our conventions. So this is if you want to phrase your induction like weak induction, which is usually the most simple way. So you have to do this bonus thing. So for natural number induction, you just have to do 0 and you have to do if n then n plus 1. So you still have to do those, right? Like to do 0 and you have to do if alpha then alpha plus 1. But you also have to do limit cases for ordinals which are not successors, like omega. Okay. And with the axiom schema of replacement, we can do recursion along the ordinals. And prove that every well order is isomorphic to some ordinal, in fact, a unique ordinal. So if we want to talk about well orders, you might as well just talk about the ordinals because every well order is realized as an ordinal. Okay, so we can do recursion, and recursion allows us to define like plus and times and exponentiation of ordinals, and they are not the same as plus and times of exponentiations of cardinals, even when those ordinals are cardinals. So they're actually different operations which are denoted the same, which is very unfortunate. But for instance, this allows us to build an ordinal called, say, omega plus omega, right? And that's bigger than all of the natural numbers. It's bigger than omega. It's bigger than omega plus n for each n, which is the supremum of that set. So we can build that. We can build omega times it. So this looks like a copy of the natural numbers with another copy of the natural numbers like stacked after it. So what it looks like. We've got omega times omega, which it looks like copies of omega stacked up like omega. So you've got an initial copy of omega sort of corresponding to 0, and you've got your one copy of omega satisfying corresponding to 1, and you have your next copy of omega corresponding to 2, and so on and so on. So you have like those, and then like we can even do omega to the power omega, which becomes kind of harder to interpret. You take the previous thing and do it omega many times. Right, so these are getting kind of long as sets, but they're all countable. And like, I mean, just for funsies, while we're here, there's actually, you can do omega to the omega to the omega to the omega. You can do that kind of forever. And by that, I mean, it's the limit as of the sequence omega, omega to the omega, omega to the omega to the omega, and so on. So you can form that ordinal. This actually has a name. It's called epsilon 0. It's important in proof theory. So this is that looks pretty big. Still countable though. So you can do lots of fun things with ordinal operations. Other fun ordinals, in my personal work, omega 1 CK, which I will just write its name down and then leave it mysterious. You can look it up if you want. It's complicated. This is countable as well, though. Anyway, so here are a bunch of examples of countable infinite ordinals. There's lots of them. Okay, so that's where we are with the ordinals. Now, keep in mind, though, why are we doing all of this? Well, we're trying to give a precise definition to our intuitive idea of the size of x is a cardinal rather than the size of x equals the size of y via bijections. Okay, so we're very nearly there now. All right. So firstly, we need a notion of something that's called an initial ordinal. Okay, so an ordinal alpha is called initial if for all beta in alpha, so that's all smaller ordinals, the cardinality of beta is strictly less than the cardinality of alpha. Okay, those are initial ordinals. So the idea is they're the first ordinal of their size, where size is cardinality. So here are some examples of initial ordinals. Every natural number is initial, right? Because, well, it's trivial for the empty set because there are no betas in alpha. And then like 1 is the set containing the empty set, right? And the only beta in that alpha is the empty set, right? And that is strictly less than 1 in cardinality, right? Because there's no bijection between the set containing the empty set and the empty set, right? And similarly 2, right, is the set containing 0 and 1, and neither of 0 or 1 as sets are in bijection with 2, right? And so on. Okay, so these are all initial. Also, omega is initial because everything in omega is finite. But omega itself is infinite, right? So there's no bijection between an element of omega and omega itself. Okay, so far everything is initial, right? However, non-examples, let's put them over here. Omega plus 1 is not initial. So that should mean it has an element which is in bijection with it, right? And that element is, of course, omega. So there is a bijection between omega plus 1 and omega. There's no bijection that preserves order, but there is a bijection, right? We could send omega goes to 0, 0 goes to 1, 1 goes to 2, 2 goes to 3, 3 goes to 4, right, and so on. And that's a bijection between omega plus 1 and omega. Okay, so omega plus 1 is not initial, and neither is omega plus 2. These are non-examples. Let me actually write that down. So omega plus 1, omega plus 2 says, and so on. Right, omega plus n for any n. Omega times omega is countable. Omega to the omega is countable. Right, these are all countable ordinals, and so they're in bijection with omega. Right, so they're not initial. Okay. So, I mean, our goal is going to be initial ordinals. Those are our cardinals. Ta-da. So we're kind of done. But we're going to get there in a somewhat meandering way. Well, it's not that meandering. We're just going to go via like one or two little lemmas. Or I guess exactly one theorem rather than one or two little lemmas. Okay, so our first theorem is that if X is well orderable, oh, I've got a chat. Well, is omega plus 1 just omega that starts with a 1 instead of a 0? No. Omega plus 1, according to the definition of ordinal addition, is this, he says, there we go. Omega plus 1 is equal to the successor of omega. Which is omega union set containing omega. So omega plus 1 is a copy of omega and then an extra guy at the top. Bigger than everything. So if I drew it, I did it in class last time, but I called everything W's. So we've got 0 at the bottom, of course, and then we've got 1, which is the next thing above 0. We've got 2, which is the next thing above 1, and so on. Boop, boop, boop. Right, and that keeps going forever. Okay, but that does not mean we've finished enumerating the set, right? Just because it goes on forever doesn't mean we've enumerated everything. That's sort of one of the major observations of set theory, right? Is that processes can be infinite in length, but not exhaustive. Okay, so that can go on forever, right? And then this set here by itself is omega. Okay, but then I'm going to add on top of everything omega itself. Right, and this is omega plus 1. Okay. And then to add 2, right, you add 2 things on top. And if you add 3, you add 3 things on top, and so on. Okay. So I said, what does the theorem say? If X is well orderable, and by that I mean there is some relation on X which is a well order, then the cardinality of X equals the cardinality of alpha for some unique initial ordinal alpha. Okay, so if there's any well order on a set at all, then that set is in bijection with only one initial ordinal. Okay, so why is this true? Okay, well, it's not the worst thing. So let's fix a well order less than of X. What do we know? Well, we know that X equipped with less than is isomorphic to some ordinal beta, right? Because every well order is isomorphic to some well ordering. Okay, so isomorphisms are bijections, right? So hence the cardinality of X equals the cardinality of beta. What's the problem? Beta might not be initial. Okay. So if beta is initial, we win. Or at least we showed existence, right? We've shown there is an initial ordinal that you're in bijection with. Otherwise, beta is not initial. But that means that there is an element of beta which is in bijection with beta, right? Otherwise, beta is not initial. So there is alpha in beta with the cardinality of alpha equaling beta. Okay, so I know that there's an element of beta which is less than it. Okay, and then not only do I know there's an element with this property, I know there's a least such element. Pick the least such alpha. Right, so there could be a bunch of different elements of beta which are in cardinality with beta. So I have the same cardinality of beta and they're in bijection with beta. So I'm going to pick the least because it's a set of ordinals. So I can do that. Pick the least such alpha. And then the claim is that the cardinality of X is the cardinality of beta is the cardinality of alpha, which is all just by definition. Right, cardinality of X equals cardinality of beta because beta's isomorphic to X. Cardinality of beta equals cardinality of alpha because of definition of alpha. And so cardinality of X equals the cardinality of alpha. And the idea is alpha is initial. Why is it initial? Well, if it's not initial, if it is not initial, there's some gamma in alpha in cardinality in bijection with alpha. But then that gamma is in beta and in bijection with beta too, contradicting that alpha is the least. Okay, so that shows existence. And then for uniqueness, right, if a set is in bijection with two different initial ordinals, then one of those ordinals is in the other. All ordinals are comparable. But then those two initial ordinals are in bijection with each other, and that contradicts the definition of being initial. Right? You can't be in bijection with any of your members. So alpha is initial, and then also alpha is unique. So these last two claims, you can fill in the details yourself if you'd like. All right, so if you have a well-orderable set, then it is in bijection with a unique initial ordinal. Okay, so that's going to be our definition of cardinal. So if X is a well-orderable set, then the cardinal number of X, cardinality of X, is the unique initial alpha such that cardinality of X equals the cardinality of alpha. Okay. So initial ordinals are cardinals. That is our definition of cardinals. And the cardinal number of a set is the unique initial alpha with which it is in bijection, right? If there is such a thing. Okay, so this is a remark. This is consistent with us calling every natural number an omega cardinal numbers. For instance, right, 7, which is the set containing 0, 1, 2, right, up to 5, 6. Right, it's initial because we've shown every natural number is initial, right, and it's in bijection with itself. So its cardinality as a well-orderable set is 7, right, which is itself. Okay, so cool. So what I've done now, we've defined the cardinal number for well orderable sets. You might be like, okay, James, that's great, but like you might be skeptical that every set can be well ordered, right? And a good question would be, like, for instance, what is a well order of the reals? Right, the standard order on the reals is not a well order, because like open intervals have no least element, right? Even though they're not empty. So if any well order of the reals is going to have to be different from the standard order on the reals, and you can spend however long that you like trying to write down a well order of the reals, and you will never succeed. It's actually very difficult to like trying to define a well order of the reals. So you might be like, okay, well, I'm still skeptical that I know what the cardinality of the reals is, because I don't know a well order that I can attach to it. So I don't even know it like can be well ordered. Okay, and that's a reasonable bit of skepticism to have. All right, so let's put that aside temporarily. We'll get back to it. And see what cardinals we can build with our definition. Okay, so cardinals we have so far are 0, 1, 2, 3, and omega, right? Those are the cardinals we've had from before. And then question is, like, can we build any other initial ordinals? Or is that all of them? Right? The definition doesn't insist that there are uncountable ones, for instance. Okay, but we can actually build something called the Hartog's number of a set. And it looks kind of complicated in its definition. And the reason is because it's very carefully trying to avoid the use of the axiom of choice. Okay, so what is the Hartog's number? Right, so if we have a set A, then the Hartog's number of A, if it exists, which we'll call H of A, it's the least ordinal alpha such that alpha is not less than or equal to, in cardinality, H of A. Sorry, why is H of A doing there? The least ordinal alpha. That shouldn't have an H. My bad, team. That should just be A. That's the cardinality of A. Otherwise, we're circular. All right, so it's the least ordinal alpha, which is not less than or equal to in size A itself. That's the Hartog's number of A. So if you work through the definitions, right, alpha, cardinality of alpha not being less than or equal to cardinality of A means there is no injection from alpha to A. Right? That's just what that means, right? Because being less than or equal to in cardinality means there is an injection. So being not less than or equal to in cardinality means there's no injection. Okay, so it's the least ordinal for which there is no injection from alpha onto A. And if you reason about a little bit, that also means it's the least alpha that is not in bijection with any subset of A. Right? And that's because a function is surjective onto its image. So an injection is a bijection with its image. So we can also say it's the least alpha such that alpha is not in bijection with any subset of A. Okay, that's the Hartog's number, if there is such a thing. Okay, so this looks like a complicated definition, so let's compute it for a few different sets. Okay, so what is the Hartog's number of the empty set? What is the least ordinal for which there is no injection from the empty set to that ordinal? Can you work it out? This is your interaction for the day. So you have to work very hard. Okay, so if you don't know, then what we're gonna do is we're gonna start with the least possible alpha, and we're gonna see if that works. And if it doesn't, we're gonna increase by 1, and we're gonna keep doing that until we find the answer. Okay, so alpha equals the empty set. Is there an injection from the empty set to itself?
I think so.
Indeed, there is, right? It's the stupid one, the empty set, right? It's a stupid, the empty function. So it's the stupid thing. Yes, there is an injection from the empty set to itself. There's an injection from the empty set to anywhere. Okay, so that means that 0 is not the Hartog's number, right? So not 0. Okay, and then let's think, okay, so 0 didn't work. So what about 1? Is there an injection from, oh, I've got my things here one way around in my little F. That's an alpha and that's an empty set. My bad. Is there an injection from 1 to the empty set?
No.
No, indeed, because there's no function at all from 1 to the empty set, right? Because there's no output at all, but you do have some inputs. Okay, so that means that the Hartog's number of the empty set is 1. Okay, now let's look at some other examples. Hartog's number 10, 26, 40. Okay, so I have this set here. I mean, the important just thing is that it has 3 elements. So it's just an example of a set with 3 elements. Okay, is there an injection from the empty set to that set with 3 elements?
Yes.
Yes, the stupid one, right? There's an empty, right? Like it's the trivial one, but yes. Is there an injection from 1 to this set? You can put it in the chat, people who are shy. Yes, right. There's an injection from 1 to the set, right? You can send, right? 1 is the set containing 0. You can send 0 to any of the 3 elements. That's an injection. Is an injection from 2?
Yes.
Yeah, right. And 3? Yes.
Mhm.
4?
No.
No. Okay, we're starting to see the picture. Thank you for playing along, Kai. Okay, so this is 3, this is 4. Okay, so based on those 2 bits of data, can you guess what the Hartog's number of n is going to be?
N plus 1.
It's n plus 1, yeah. Because n has n elements, right? We very carefully picked the natural numbers to be defined this way, right? So there's no injection from a set containing n plus 1 elements to the set containing n elements. Okay, so good, right? So if we have a finite set, then the Hartog's number is the size of the set plus 1. It's a theorem you can prove. Harder question, what's the Hartog's number of omega? So let's think. Is there an injection from a finite ordinal n to omega? That's not a bad guess, Ivan.
Yeah, any enumeration of omega or any version of omega is going to be countable. So.
Yes, indeed, right? So yeah, like all the finite stuff, there's an injection, right? The identity works. Omega is in bijection with itself, right? So it's not omega, but also it's not omega plus 1, because that's countable. And it's not omega plus 2, because that's countable, and it's not omega plus 3 because that's countable, and so on, right? So whatever it is, if it exists, number of omega is necessarily uncountable. Because any countable ordinal is in bijection with omega, right? So there's an injection from that ordinal to omega, right, which is given by the bijection. So if the Hartogs number of omega exists, then it's some uncountable ordinal, right? And we haven't come across any such fellows yet, but we're about to. So first claim. Oh, sorry.
Sorry, would we call it like Aleph 1?
We do indeed call this Aleph 1. Yes, that is the set Aleph 1, exactly. Yes, Kai, very good. You can also call it Omega 1 if you prefer, but yes, this is Aleph 1. So yes, anticipating the answer, this is going to turn out to be the set Aleph 1. This is the first uncountable size, which isn't obvious from the definition, but it is true. Anyway, what's my theorem? Theorem says, okay, if it exists, then the Hartogs number is an initial ordinal. Okay, so let's prove this. All right, so claim. So let's suppose that the Hartogs number of A, H of A, is some ordinal alpha, and let's suppose that beta is in alpha. So what we want to show, we want that the cardinality of beta is strictly less than the cardinality of alpha, right? Because that's the definition of being initial. Okay. Well, what do we know about beta? Well, as beta is in alpha, then there is an injection F from beta to A, right? Because alpha is the least ordinal such that there is no such injection, right? So any ordinal less than alpha has to be true there is such an injection, right? Otherwise, alpha is not minimal. Okay. So if the cardinality of beta equals alpha to a contradiction, then there is an injection G from alpha to A, right? And how does this injection go? Well, it goes, let me draw a little picture, right? Alpha goes to beta via the fact that their cardinalities are equal. And then beta goes to A via F, right? And the composition of these two is G. Right, so this is an injection. So that means that this function G is an injection from alpha to A. So hence, well, or contradicting that there is no such injection, right? That's an injection that contradicts that there is no such injection. Okay, so if you've got an element of a Hartogs number, right, you've got an ordinal less than that Hartogs number, then that is strictly smaller in cardinality. Okay, so technically, okay, I should be careful. Right, what I've shown is that cardinalities aren't equal, but of course, cardinality of beta is less than equal cardinality of alpha because beta, by the identity, by the inclusion map, right? Because beta is also a subset of alpha because of transitivity of alpha. Okay, so it's less than or equal to for free. I've just shown it's not equal. So it's strictly less than. Hooray. End proof. Boop, 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 boop. All right, so if the Hartogs number exists, then it's an initial ordinal, meaning it's a cardinal, right? Because that's what we've defined cardinals to be. And then, so the big, great. Now the theorem, now we would like to prove that there is a Hartogs number for every set. Do you want to take a break now? It's 9:40. I think this is a good time to take a break. Let's just pause, and then we can reconvene. Remind me to unpause the recording. It unpaused. We need more light on my face. You all want to see my face better? It's a real question. About that. Lord. There we are. Okay. Hartogs number exists for every set. Okay. So the idea here is it's not too hard, actually. It's just let's collect together all of the ordinals which inject onto A and claim that that's the Hartogs number. Okay, so let S be the set of alpha ordinals such that the cardinality of alpha is less than or equal to the cardinality of A. And so the claim would be, sorry, that S looks a lot like a delta, right, doesn't it? Which is not intentional. Not too bad, though, because delta is a word for an ordinal. So claim is that the Hartogs number of A is equal to S, right? That's the claim. Now, how would we show that? Okay, so firstly, we need to show that S is an ordinal. Okay, so how would we show that? So we need to show, technically, right, we need to show it's transitive, and we need to show it's well ordered by the element relation. But we get the second one for free just in virtue of it being a set of ordinals, right? Any set of ordinals is well ordered by the element relation. There just might be some gaps, right? And that's because all ordinals together are well ordered by the element relation. Okay, so S is well ordered by element as it is a set of ordinals. Why is it transitive? Well, if alpha is in beta is in S, then the cardinality of alpha is less than or equal to cardinality of beta, right? Because alpha is a subset of beta. We can use the identity function. And that's less than or equal to the cardinality of A by assumption on beta of beta being an S. So cardinality of alpha is less than cardinality of A. So it's transitive too. Okay, so S is an ordinal. Cool. And then we want to show it's the least ordinal, which does not inject onto A. Okay, so first we need to show that S does not inject onto A, and then we need to show this the least such thing. Why does S not inject onto A? Or another way, why is the cardinality of S not less than or equal to the cardinality of A? Okay, well, if the cardinality of S was less than or equal to the cardinality of A, then as S is an ordinal, that means that S satisfies the defining property of S. So S is in S. But that's a contradiction because we know no ordinal has that property. Okay, so cardinality of S is not less than cardinality of A. And why is it the least? Well, if alpha is in S, then cardinality of alpha is less than or equal to cardinality of A by definition of S. So no smaller ordinal satisfies that the cardinality of alpha is not less than or equal to cardinality of A. Okay, so S is the Hartogs number. But I have made one very, very minor assumption right at the beginning, is that I built the set S. And the problem is I've defined it by a property, right? It's a collection of ordinals less than or equal to in cardinality the set A, but I haven't given you a bounding set. I've given you a bounding class, right? I've told you it's all of the things which are ordinals, which have the property that they're not less than or equal to. This is not a bounding set, it's a bounding class. Right? Because a set of all ordinals is not a set. So this is not an application of the axiom of separation, even though it looks like it, or the axiom of subset, sorry, I call it subset in this class. So how do I build S is the question. And we can't do it by the subset axiom, actually. The subset axiom will not help. We need to use replacement. Okay, so the idea is to build S. How do we do this? So what we're going to do is build this directly by replacing subsets of A with the ordinal alpha that injects onto A. Okay, to build S. Okay, so firstly, let X, which is a subset of the power set of A cross A, be the set of well-ordering relations of a subset of A, right? That is a set, right? Because it's a subset of a is any subset of the class of ordinals a set? So, I mean, a subset of the class of ordinals is a set because you've said the word set. Any collection of the class of ordinals is not necessarily a set, Kai. For instance, the class of all ordinals itself is not an ordinal. Even if I take out 0, no. not just proper isn't enough. The thing that does make this true, and in fact is the equivalence, is it needs to be a bounded subset. So if you know there's a biggest member, or at least not necessarily biggest, but there's an upper bound. So there's an ordinal such that no thing in your collection trying to build is bigger than that. That's enough. It needs to be bounded.
Like a maximum.
It doesn't. The thing is, it's not necessarily maximum because there's not necessarily maximum ordinals.
Mm-hmm.
Like, for instance, the collection of all finite ordinals has no maximum, right? But it has a bound, which is omega. So it's very nearly the maximum. It's just because there aren't necessarily any maxes, but we can take the soup. Okay, so what we're going to now, we have our set X. So using replacement, replace an element of X with the ordinal ORD it is isomorphic to. This is S. Okay, so remember, replacement says if I can tell you a formula for like 1 by 1, saying here's an input, here's the output. It's not necessarily a function because it won't be a set, but I have a description for this, right? I can write down what you should do. And our description here is, if you are a well-ordering relation, I'm going to replace you with the unique ordinal you're isomorphic to. If you're not a well-ordering, I don't know, you spit out the empty set. I don't care. So that process satisfies the axiom of replacement. So I can replace the collection of well-orderings of subsets of A with the ordinals of those same lengths. And that's going to be S. Okay, so that looks very complicated, and it is because we haven't used replacement very often. In fact, I only introduced it last class. The idea is just we're taking subsets of X well-ordered somehow, and we're going to take all of the ordinals sort of that are of that length, collect them all together. Those are going to be all the ordinals which are in bijection with a subset of A, which means they inject to A itself, which means it's S. Okay, so cool. So what we know now is the Hartogs number exists for any set. So, for instance, going back to our little omega example above, and the Hartogs number of omega is the set of ordinals which are less than or equal to cardinality of omega, which by definition is the set of countable ordinals. So that's the Hartogs number of omega. And necessarily, this is equal to the least uncountable ordinal. And the key idea is we actually know this is a set using replacement. Okay, so this is complicated. What does it let us do? Well, it lets us, and I put this here in italics, it's important, without the axiom of choice, because people are still worried about choice sometimes, to build an increasing sequence of initial ordinals. So finally, we get to define the alephs now. So we define cardinals, but we get to define alephs. So using transfinite recursion, that thing that it's like the recursion. I'm telling you how to index a process by ordinals of infinite initial ordinals. So the first one, omega 0, that's just omega. So the first element of my sequence is omega. If I tell you what omega alpha is, how do I work out omega alpha plus 1? How do I work out the next element of my sequence? Well, it's the Hartogs number of omega alpha. Sorry, not alpha plus 1. That's circular. And then if alpha is a limit, then you have to do something irritating, which is take the supremum. So you take the union over the beta less than alpha of h of omega beta. Okay, so what does this mean? What are the first few values of this? Okay, so omega 0 is omega. Omega 1 is the Hartogs number of omega. Omega 2 is the Hartogs number of the Hartogs number of omega. Omega 3 is the Hartogs of the Hartogs of the Hartogs of omega, and so on, right? And then, so that works for any finite number, but then also omega sub omega is equal to the supremum of the set containing omega, the Hartogs number of omega, the Hartogs of omega, and so on. And then omega sub omega plus 1 is the Hartogs number of this big supremum, and so on. So this can keep going. Okay, and these are cardinals of increasing size, right? Because each Hartogs number is an initial ordinal. Each initial ordinal is a cardinal. So the cardinality of here, they're getting bigger as we go, strictly bigger. Okay, so cool. Usually, as we see at the bottom, instead of using, usually is. In modern set theory, I think modern set theorists actually do use omegas here, but slightly less modern set theory, these are the alephs. So this is aleph 0, this is aleph 1, this is aleph 2, this is aleph 3, this is aleph omega. So if you're wondering when this notation would come up, this is how we formally define it. And how we get the set theory to prove that this exists. It means what you think it means, though. Omega 0 is the countable cardinality. Omega 1 is the smallest uncountable cardinality. Omega 2 is the second smallest uncountable cardinality, and so on and so on and so on. Okay, so let me make that precise. I don't know if I want to prove it. All right, so the first claim, for every alpha, omega sub alpha, or aleph alpha, if you prefer, is an initial ordinal hence a cardinal. And if capital omega here is an infinite ordinal, then infinite initial ordinal, I need initial, then omega equals let me use little omega alpha for some alpha. So my claim here is this list of ordinals of that we've just defined, right, by taking omega first, then the Hartogs number of it, then the Hartogs number of that, and so on. That's actually an increasing list of every single initial infinite initial ordinal. They all get caught eventually by this list. So let me put that in a black box for the moment. We might come back to it at the end of class because there's some stuff at the bottom that I'd like to make sure I talk about before I get into this proof here. So the idea here is that this list that we just made via the Hartogs number is a complete list of everything that I have called a cardinality. That's infinite, sorry. All right. So let me clear up the end, and then we can go back to that theorem. Okay, so remark. Thus, the sequence of omega sub alpha is a sequence of infinite cardinalities written in increasing order, and we often call these alephs, right? And we write see that's the real way of writing it. It is so hard, man. Like, you have to do like 8,000 separate strokes here. Look at that, so difficult. So usually we write aleph alpha instead of omega alpha because I don't know. People hate me and make it hard to write things. There's also Beth numbers and Gimel numbers, which are further letters in the Hebrew alphabet, which are other lists of cardinals, which are potentially different depending on, well, they are not provably the same. Okay, so back to that earlier thing about the reals. So question. So we've defined the cardinal number of any set that can be well ordered, right? Because it's the unique initial ordinal that is in bijection with you. And we've listed all such cardinals. Is this all of them? Or are there sets that can't be well ordered, in which case I haven't told you what their cardinality is yet? So one thing that would satisfy this is the well ordering principle in this box here. So the well ordering principle says every set can be well ordered. Okay, so what do we think of this principle here? I've called it a principle rather than a theorem because of historical reasons, but here's the status of this claim: every set can be well ordered. It's equivalent to the principle, is equivalent to the axiom of choice. So this is one of there's usually three main ways of stating choice. There's Zorn's lemma, which everybody hates. There's the one involving choice functions, right? If you have a collection of non-empty sets, there's a function that takes in each of one of these sets and spits out a member. And there's this third one: every set can be well ordered. Those are the three standard ways to talk about the axiom of choice. Okay, so if you like the axiom of choice, then I have listed all of the cardinals for you. If you don't like the axiom of choice, then I haven't listed all the cardinals for you. But then you're in a funny situation where you need to deal with these sets, which are necessarily a little bit weird, right? Like, if we can't build a counterexample to the axiom of choice, because then we'd show the axiom of choice was false. So anything that like contradicts choice somehow has to necessarily be strange. And you have to talk about like what the cardinal of that thing would be. And it is possible to like give a definition of cardinal for such things, but it's quite complicated. So find a definition that works for non-well-orderable sets. It can be done though. Okay, so the summary, we finally defined the Aleph numbers, right? So we now know what the cardinality of a set is. So take a set, the cardinality of that set is the least ordinal that it is in bijection with. That's it, if there is such a set. And as long as that set can be well ordered, or assuming the axiom of choice, that is legitimate for all sets. So the cardinality of R is whatever the least ordinal is, which is in bijection with R. I don't know what that is, because that bijection would give me a well ordering of the reals, because its cardinal is an ordinal, which is well ordered by the element relation. So I can move that bijection. Sorry, I can move that well order through the bijection. And we've already talked before about how it's hard to define a well ordering of the reals. So like, still open question. Like, what's the value? What alpha goes in here? We know it's not 0, because that would be countable. Could it be 1? Can it be 2? Can it be 3? Continuum hypothesis says it's 1, but that's independent of all of the other axioms, including choice. Okay. Chat. Are omega and omega plus 1 isomorphic? They are not isomorphic. They are in bijection, though. That's the thing. So we have to, yeah, this is the irritating thing about cardinality. So we have ordinals, and they are often in bijection with each other, but not isomorphic. So there's no element relation preserving isomorphism. Sorry, bijection. So that's the thing we have to keep in mind. Okay. Let me prove I don't know the first claim of this, because it shows you an instance of transfinite induction, and then I'll let you all go. So for each ordinal alpha, omega such alpha is an initial ordinal, hence a cardinal. Okay, so let's do this by induction. So alpha equals 0. Then omega sub 0 is just omega is initial. Right, we already showed that above. Successor case. Here you don't actually even need induction. So omega alpha plus 1 is equal to the Hartogs number of omega alpha. And we've already proved all Hartogs numbers are initial ordinals. Right? So that's initial. But now we need to do the non-zero limit. So suppose beta is a non-zero limit. Then omega sub beta is equal to the union over the alpha less than beta of the Hartogs numbers. So of the Hartogs numbers, I mean, it is of those, of omega sub alpha. Right, and then the claim, what we have to show, this is initial. All right, so how do we do that? Well, it's funny, it looks actually kind of like an argument from real analysis, because it's about supremums. Okay, so suppose like gamma is less than omega sub beta. Okay. Then gamma is less than omega sub alpha for some alpha less than beta. By definition, sort of the supremum. Right? If you're less than this, right, the supremum, omega sub beta, is the least ordinal greater than or equal to everything. So if you're less than the supremum, then there's something you're not greater than or equal to, which means there's something you're less than. Okay, so that means alpha is less than omega sub alpha. Okay, but then as omega sub alpha is initial, that's our induction hypothesis coming in. Cardinality of alpha is strictly less than the cardinality of omega sub alpha. But of course, this thing is greater than or equal to, sorry, less than or equal to the cardinality of omega sub beta, as omega sub beta is a superset of omega sub alpha. So hence, cardinality of gamma is strictly less than cardinality of omega beta, and omega beta is initial. Okay, so it is not especially important to me that you understand the details of this proof, but I do think it's important for me to show you like one or two arguments that go by transfinite induction. Right, so I'm doing induction over all ordinals at once here, right? And the thing that makes it different than induction over the natural numbers is this case here, where we have ordinals which are not successors. Okay, team. Here endeth the lesson. So next class, we'll actually tidy up. We're going to talk about sort of the universe of sets, the von Neumann universe. We're going to finally introduce the axiom of foundation. Hooray! And then we'll have all of the axioms of ZFC, and I'll talk about, I don't know, topics in advanced set theory. So I think here's sort of the end. I don't know if any of this stuff would be examinable. It depends what I decide to talk about on Thursday. But if that's the end of class, so feel free to pop off. If you have any questions, there's 2 minutes left. Have a good day.
Thank you.
No problem. Oh, chats. Is there an exam review session? I'm going to be holding office hours in the whatchamacallit study period. So those will function as review sessions. And that you can come and talk to me about it, about the exam. They'll probably be on Zoom as well, because I'm in DC. Fine, you just AFK. Would you have a question?
No, thank you. Bye. Yeah. See ya. Bye-bye.